Alright, welcome back, you guys. So, this is our part 2 of Structures of Metals. Structures of Metals. Just making sure I had the chapter. So, chapter 1, finishing up the lecture. Alright, so we're back, should about be halfway through at this point, maybe a little bit more. So maybe not quite as long of a video. But we left off last time with hot worked versus cold worked. And we started going over the the structures of the metals, right? So we're going back, we look at dislocations, we were talking about crystal structures, right? And there's going to be a video, and I actually took some of these, this figure here, from the video that you'll be seeing here. This will be in between lecture 1 and lecture 2 this week. It'll probably be incorporated with lecture 2 actually, because since it covers more structures of materials and properties of changing the structure, or what that structure means. Alright, so hot worked versus cold worked. So it's to understand the differences here, it's rather important to understand them. We have hot worked metals versus cold worked metals, and we use these at various times while we're either creating machines or doing machining or so on. So there's a range here. Really kind of gives you whether a part is cold worked or hot worked, or also you don't really hear this term too much, but it's warm working. So these are the temperature ranges. So when you say something's cold worked, this is a good example over here on the right hand side. It's going to be this ratio of the temperature over that temperature, material's melting point temperature. So this is a ratio or percentage towards that melting point temperature. So in this case, our cold working is 0.3. So we do under essentially 30% of your temperature reached up toward that melting point. Warm working between 0.3 and 0.5, so 30 and 50% or so. There toward, again, overall being that melting point at 100%. Then hot working, anything that's greater than 0.6% is considered to be hot working. Now, why does that matter? And it actually, we'll see why that matters here. With hot grains and cold worked grains, they end up essentially forming differently. And one of the main things here is when those crystal structures form and create new growth. So the hot rolled grain changes, or hot worked items, hot rolled metal is held above its recrystallization temperature, so that's that range. So typically when you're hot working something, when it cools, it's been above that recrystallization temperature. So what you're seeing in the actual PowerPoint right here is an example of this. So wrought product with large grains. So we have a rather high grain material here. And this is brought through rollers. So, this is our rolling press, or this is our rolling press, and we're trying to get the metal to be a certain width, right? So we have hot rolling being done here, and if you notice, the grains are rather big, and then they get stretched. And this is a term called I get this one mixed up a lot. Isentropy. So it's kind of a mouthful to say sometimes, but basically what it means is you don't have the same direction in grain. It's not equal. So you get a stretched grain. So stretched in one direction, or what they tend to say is one axis, rather than being uniform in all three axes, X, Y, and Z. You end up getting this stretched material in one direction. But when it's hot, when we're doing actually hot rolled or hot worked, we actually are again above this recrystallization temperature. So what that does is it regrows those crystals. So this is what's happening in here, is showing new grain starts growing, and then by the time it cools even more, it's basically recrystallization has been completed. So this is an example of why hot worked is different than cold worked. So cold worked, basically one of the main things that happens during cold work that doesn't happen during hot worked is something that's called strain hardening, also termed cold working. And this is something we're going to be doing, not actually a 2-week period now. It'll be about 3 weeks from now. We'll be doing some cold working using our cold roller. We'll actually roll out some various different pieces of metal, and we'll see how those interact. How does that affect the hardness of the metal, the properties of the metal? So strain hardening is a phenomenon by which ductile metals become harder and stronger as it plastically deforms. So it's getting stretched out, and this is another example here. And if you notice, there's no regrowth of those grains, so you end up getting that elongation of a grain. Anisotropy of metals happens. I thought it was one of these slides here. We'll go over that term here soon, and I'll show you how to spell it and everything. But basically, we get one directional growth, kind of stretched in one direction and not the other, or in this case, flattened out, right, like a pancake. You can think of it. So during cold rolling metal causes strain hardening, which changes the material properties. So cold rolling mechanical changes that you'll see is an increase in hardness and stiffness. So you can't really puncture it as easily. It doesn't bend as well. But what it does do really well is you're able to get a good, hardness out of it, and you get a better stiffness. So, I mean, ductility goes down. It depends on what you really want for the material, right? You could, I guess, say one way or another, hardness is good, hardness is bad, depending on what you want it to be, or stiffness and ductility, right? Spring, we want ductile, whereas a knife, you're going to want that rather stiff, right? You're not going to want your knife flexing and bending as you're trying to cut with it. So really, whether it's better or worse, but what you're going to see from cold work is as you do cold work, it's going to get harder, and it's going to get stiffer, right? The stiffness is going to increase. So it's going to bend more. Bend resistance is going to go up. Puncture resistance is going to go up, but that ductility is going to go down. So it's not going to be able to stretch more. And what happens typically with that is as it gets more and more stiff, the more and more brittle it gets, right? So, it can potentially get a little bit more brittle. So you end up getting more of a cracking rather than a bending action, right? If you flex it too hard or too much. And again, it depends on how much work you've done. And we'll actually see this in the next lab, not this upcoming lab. All right, types of defects in single crystal lattice. So what they mean by single crystal lattice is, you have a copper or an aluminum, single crystal, essentially. Within that structure, you have only aluminum, so you can think of the blue. We'll just think of it as aluminum. Blue as aluminum atoms, right? And they're, making that metallic bond with another aluminum atom. And what we get here is that you think of the BCC cubic structure. We have this atomic structure going on, right? So what happens when we get a defect in there, right? So in this case, what are the defects? Well, we have a self-interstitial atom. So this is in say one crystal within a structure. So I'm go give you an example here. So like this would be considered part of that crystal. This is what I was looking for. So this would be considered, say, a crystal within a crystal lattice, right? You get a grain boundary, and then you get another crystal. All right, so get back to here. All right, so defects. So within that crystal structure, right, we end up having self-interstitial atoms. So basically, an atom gets crammed in there, and it's pushing out, right? So it's actually creating stresses that will want to push this out. So it's a self-interstitial atom. Basically, it's itself shoved in a spot where it essentially can't fit very well. Substitutional impurity atom. So we have an impurity that's in there. So that could be another defect in, say, a single crystal lattice. We could have a vacancy. So this is where an atom's missing. And again, that's going to cause stresses within the part. So you could think of this as like weather, if you're thinking in weather patterns, or but you could kind of think everything's kind of want to push in here, right? Pressure kind of wants to push in there. We have a vacancy, so we want parts want to fall into that spot essentially. They're being obviously held back by other bonds, so again, this creates a stress within the crystal itself. Interstitial impurity atoms, so this could be, again, another impurity in there, kind of like the substitutional impurity. Substitutional takes the whole place. Institutional impurity kind of fits in between, so institutionalized or surrounded by those in this case aluminum atoms that we've talked about, right? So those are the main types you'll see. 4 main types of single crystal lattice defects that you tend to see, and why they're important. So within all those crystals, we get these impurities. It's almost impossible, not really impossible necessarily, because in labs they do it, but to grow a perfect crystal, right? So what happens because of those impurities, right? So structural sensitivity versus structural insensitivity. What's the difference between the two, and how does it affect, say, the part itself? So this is rather important, again, for engineering purposes. We have structural sensitive properties, are properties that are affected by the presence of defects. So those defects actually affect the properties themselves. So these mechanical and electrical properties of metals, so this could be really an electrical property, mechanical property, so things such as yield stress, fracture strength, and again, electrical conductivity. So those are the structural sensitive properties. So if there's a defect in there and it affects those are termed to be structural sensitive properties. Structural and insensitive properties are not affected by the presence of defects. So this is physical and chemical properties such as melting point. So metal's still going to melt at the same point even though it's got defects in there, right? Specific heat isn't going to change, and that's a property we'll talk about, especially when we get into fluid mechanics, next year. But we'll talk about it a little bit more this year as we go through. Coefficient of thermal expansion. So again, it has to deal with that melting point and the specific heat. So how much a material will expand when it's warming up. Elastic constraint. So how elastic that material is, such as modulus of elasticity, which we haven't talked about yet. That's next chapter. And modulus of rigidity. So those are structural insensitive properties. So those aren't, again, affected by the presence of defects. So what do those defects really do? Well, you look at the crystal again, in this case, 3D fashion, we have dislocations in the crystal. And this dislocation, again, could be due to, say, an extra atom being shoved in there or a missing atom in there. And what you'll end up seeing is, you get this structural pattern because an atom bonds with an atom, which bonds with an atom, and so on, right? You get that BCC structure. Well, in this case, you end up getting either one missing or one gets added, or you get a defect essentially in that crystal structure. And these are two different types. So this is one here is called an edge dislocation. So here we have essentially an edge running down the center of this part that dislocates and spreads that, and essentially mushes kind of two atoms together. And what we'll be talking about next here is we'll talk about how this adds, again, stresses into the part like I mentioned earlier. Screw dislocation, so it kind of does like this spiral staircase. Um, another example. So those are two common ones you might see. So why are those dislocations and those stresses important? So those stress concentrations at dislocations, they cause these push-pull kind of stresses within the atomic structure of a metal, that bonding. So here strength is increased by making dislocation motion difficult. So again, you have that push-pull action. What actually happens here is you end up getting, say, two dislocations, right? And this happens common enough in your materials at the atomic structure when it's creating all these atomic crystals, metallic crystals here. But you get a lot of these dislocations. So what happens is you end up getting, this push-pull effect again, and they don't want to cross. So trying to get two dislocations to cross, it just doesn't happen easily. And because of that, cold work causes these dislocations to become crammed together. So the more crushing force you do, more squeezing of that metal you do, you're actually taking those crystals and kind of rearranging them with plastic deformation. So when we actually plastically, permanently deform a metal, we're actually doing cold work to it. So these get crammed together, creating a metal with higher strength. So we look at, I like this picture. This one comes, I believe it's in the new book, which I gotta make a video about here still. But we have this picture here in this of titanium alloy here after cold working. What you actually see here, and they talk about it a little bit in the book, but you can think of these as these are the dislocations. So what you're seeing is these get entangled, right? So after cold work, all these edges, and I think of them as like hairs or different things, they get crammed together and they don't want to pull apart. So these dislocations entangle with one another during cold work. Again, these are like edge dislocations. You can think of that being an edge. So just getting those to pass each other, difficult. And again, the more work you do, the more cramming material together, the tighter pattern, the tighter of this cold work you're going to get. And again, that's going to keep it from wanting to pull apart. Sometimes the dislocations aren't a good thing, right? So yeah, it's great because it can help increase strength, increase your rigidity. But in certain times you could have, say in this case, I'm not sure, you're pushing steel ball against a sheet, and they're trying to create this dome, right? And what's happening is it's cracking right here, right along one of its dislocations. So it's basically that dislocation has caused a split. And again, this case is aluminum sheet with a crack, vertical dark lines at the center, and you can see it develops a bulge. So this is a bulge test, and the rolling direction of the sheet was vertical, so you end up getting, as it bulges out, it just basically cracks right along that defect. So they can also basically be a stress point, and as soon as that stress point's not able to take anymore, it's going to crack. Alright, so that being said, now we start looking at material properties versus cold work. So what happens as material? What happens to material properties as you do cold work, right? So we mentioned strength increases, so puncture resistance, right? Rigidity increases, ductility goes down though. So that yield strength, and yield is again where that metal starts stretching, plastically deforming. Tends to, after you hit the yield point, you're going to be permanently deformed if you keep applying stress. So that's what this is looking at. So where does it start again to be permanently deformed? Tensile strength. Usually they call this ultimate tensile strength. because this is the max amount of materials actually able to hold in that stretching process. So when we do those dog bones that we talked about in lab for the tensile tester, it pulls those dog bone looking metal pieces apart. And what we get is first we were able to see when it starts yielding, and we also get to see when its ultimate tensile, or what its ultimate tensile strength is, as well as its ductility. So we actually get to see all three of these properties with a tensile test, which is why they're so readily used out in industry for various different material properties, getting those properties, actually understanding them and knowing what they are. So we have yield strength. Tensile strength is again where the ultimate strength that it's able to hold, and then the ductility is how much it's actually able to stretch before, again, you hit that plastic deformation. And what we can see here is as we do more cold work, right, depending, these are 3 different samples here, copper is going to increase, basically each of the metals is going to increase in yield strength, so it'll start essentially plastically deforming at a higher load. The tensile strength here, again, you're able to hold a higher load before we actually start. Well, we'll get into what happens after ultimate tensile strength, but essentially part keeps stretching. But again, we can hold more strength with that, if you think about that dog bone, metal dog bone piece. Should have had a picture of that up here. And then ductility. Really the measure of ductility here is, well, in this case, percent elongation, but that's typically seen with modulus of elasticity, which we haven't really talked about yet, so I'm not going to go into that too much, but ductility has to do with the rigidity. So again, if rigidity goes up, ductility is going to go down. Alright, so again, as we're doing cold work, we end up having these internal stresses. So we talked about stresses with interstitial atom sites, atomic sites, thinking at the atomic level. Now, what does this kind of build up to at, say, the larger level? Here, the macro level, micro, macro. Basically, what are we doing to the stresses in this part? And this is rather important especially when it gets to machining, right? So residual stress is developed when you actually do the rolling itself. What you're doing is you're actually trapping tensile and compressive forces right into your piece. So yeah, you can get a pretty high precision when we talk about cold work and hot rolled and cold rolled. But one of the nice things about cold rolled is you can actually get a pretty nice precision on it. So the material's not still shrinking as it recrystallizes when it's hot, right? So that's kind of nice. You can get really good precisions on it, but if you were to take that and then machine it, not only is it have a higher strength, meaning it's harder to cut, right, with your end mill or bits, it's also got these internal stresses. So you cut off, say, what I usually talk about here is if you cut off this top sheet, right, just half of this thickness, what's going to actually happen is whole thing's going to want to bend, right? So we'll end up getting this warping, and it'll actually kind of bend and warp. And I've talked to machinists before, and they've seen this. Actually, you could physically, I guess, watch this. Unfortunately, I haven't found a good YouTube video. I'll have to look again this year of this happening. But apparently, as you cut it, you can actually see that piece flex. And that's all internal stresses created when you're actually, again, doing that rolling process, that cold work. So cold work adds residual stresses developed during rolling, or really any cold work is going to develop internal stresses. Now, that's a pretty big problem, especially for machinists, right? So say they get a piece of cold worked metal and they do need to machine it. Well, how do you actually machine that without, say, it warping, or say without breaking too many bits because it's, say, been heat treated to be a high strength, right? We haven't talked about heat treating yet, but basically you can increase that strength, that puncture resistance. So this makes it harder to machine. So one way to do that is relieve stresses. And again, we'll talk about this a bit more detailed when we get to heat transfer, or not heat transfer, heat treatments. But relieving these residual stresses is done through what's called annealing. So this is typically conducted after cold working because they want to relieve those stresses. So what you do is you put it back in the oven, and what this is showing over here is really, I mean, you can look at this. This tells you what's going to happen to the properties of the material. But over here you can see we have those long, elongated grains there. And what happens is we get that new growth. So reheating it back up does essentially what happens at the end of hot work parts. You know, it regrows those crystals and you get new crystal growth, and depending on how hot it is and how long you leave it in the furnace, you'll get larger and larger crystals, making it more and more ductile. But what you'll tend to see is when it gets more ductile, it's exactly doing what the opposite of cold working is doing. So your strength and hardness, so that puncture resistance and stiffness goes down, and ductility goes back up, right? And you can also see residual stresses in the part go to zero. So this is really what annealing is used for, relieving stresses, regrowing crystals, basically bringing it back to its original material properties. And again, that depends on how accurately you run your annealing. It's quite a scientific process. It's actually material science, so a whole different degree there if you're really interested in this. Excuse me. All right, so solidification of the molten metal. So how do those crystals grow? How do they form? Well, we've talked about the vacancy sites and everything, how electrons grab on and make these metallic bonds. Well, during solidification, right? So basically what happens, you heat up a metal hot enough, those atoms start shaking around so fast that they turn into a liquid, right? So once that starts solidifying, so we cool that molten metal back down, we have atoms slowly start solidifying or stop shaking, right? 'Cause you can think of energy being added, just how much an atom's shaking. That atom slows down, and then while it slows down, others also slow down, so the whole thing's starting to lose energy, right? When that happens, this is where those electrons start trying to share with their local, say aluminum, if we're talking about aluminum again, they're shared atoms, right? So when those grow, they just keep on tacking on to, say, the original and group up. So they're grouping up into their formation of the BCC or FCC crystal structures that we talked about. And they keep growing. They keep growing and they keep growing. And eventually those growths will actually hit another crystal, right? So we end up getting these crystals hitting each other, and eventually we get grain boundaries. And this is what we get when we solidify a metal. Now, as I mentioned, depending on how long we hold that temperature, we can actually grow those crystals. And we also look at crystal size. So crystal size is actually a standardized number format to that. And we're not going to get too far into this, but this is something that's done in manufacturing, right? So if you're a material scientist, one of the things, if you wanted a specific property of the material, strength, hardness, ductility, electromagnetic conductivity, what are you going to do is you need to make sure that, again, you're consistent with crystal size, defects, and there's a whole range I'm probably not even necessarily, I'm not really familiar with, seeing how, again, it's a totally different 4-year degree material science. There's a lot of different materials, and metals rather complex. So we're looking at a kind of the high level, kind of looking down, just getting a vague idea, understanding of how metals interact and how they kind of work with manufacturing processes. So when all is said and done, you know, those crystals that you see, we'll go to a picture, and I think we're in the very beginning. Sorry for the scrolling. Where was one? Ah, here we go. So again, this is what those crystals look like. So we have a full crystal structure, and you can see those grain boundaries. So this is at 300 micrometers. So is that point? Well, if it's this 300, it's 0.303 meters, right? So really, really, really small, thousandths of a meter, and you can look at that crystal structure. All right, so back to the end. Again, sorry for all the crazy scrolling. So the summary here, there are three basic crystal structures of metals. The two main ones, body-centered cubic and face-centered cubic. And then the hexagonal closed-packed is the third. A little bit more complex, but we mentioned the different types. So there's a lot of different, those are the three main types. Two more so, the BCC and FCC. And it would be good to be familiar with those three types. And actually, it's going to be one of the questions here. Probably going to get at the summarization of the lecture quiz. So plastic deformation in metals takes place by a slip mechanism. So that slip mechanism we talked about, you have the slip plane, and atoms kind of slip, and then they reattach to the next atom in line, and so on down the line, until eventually we get a catastrophic failure. And just a reminder, when that's slipping, that's called plastic deformation. And again, it's something we'll talk about again, but good to remember the terminology there. Dislocations become entangled with one another or are impeded by barriers such as grain boundaries, impurities, and inclusions. So these impurities create an increase in overall strength, hardness through work hardening and strain hardening. So really any impurities in there, again, those impurities don't like to pass each other. They don't like to slip, say, an atom past an atom and then reconnect to the next atom. What they're actually doing is kind of coming to an end and hitting a wall, essentially. It can't move through that. And once I do, essentially that's where it starts catastrophic failure. So that's why they're able to hold more. They don't stretch as much, right? So they're less ductile. And this is all done through work hardening or strain hardening. Grain size. I typically mention this through this, and I think this also is mentioned on the video I'm going to show. But grain size, typically you see small grains create stronger metals, while larger grains create more ductile metals. So the exception of excessively large grains, which create a really brittle metal. So I'm talking about, say, iron, for instance. So iron with really small crystal structures, they'll create a rather dense, rigid metal. The larger those grains grow, the more ductile it'll become, and the less puncture resistance it'll have. This kind of falls out when you start thinking about cast iron, for instance. People that use cast iron, especially the older cast iron, you probably had broke on you or essentially shattered. Those are really large crystals, and eventually, you get kind of to where it's really easy to break. They kind of crack rather easily. But in this case, we're talking about the same type of crystals. So iron crystals versus another iron crystal, or aluminum crystal versus another aluminum crystal. The smaller the grains, the stronger it is, less ductile it is. The larger it is, more ductile, but less strength, less puncture resistance. All right. Last two here. Metal deformation below its recrystallization temperature is cold work. So this is where it creates strain hardening. It causes an increase in strength, but a reduction in ductility, like I mentioned. And the effects of cold work metals can be reversed through annealing to relieve stresses. So that's a summary of really what I wanted you guys to get out of this chapter, the two parts video that I had. Any questions on this material, please let me know. If I forgot to mention something, or didn't explain something well enough, again, please let me know, and I can either create an extra video for answering questions, or we can meet over Zoom, or just chat through an email. Here are the references, and if you look, just to give you an idea, the way I do references here, and it's, I guess, it varies, I guess, depending on the reference, but if you see the number, for instance, at the very beginning I do this. So reference 4, reference 3, so those, where I get those pictures and that information, where I, next to the reference that I give, I typically like to give a number. Then you can go right to the web page and kind of see where I got that information from. Alright, again, any questions, let me know. Otherwise, I'll be talking to you guys in the next lecture, which I'll be posting here in a day or two. I'm going to give a little bit of time in between lectures, since typically we have 2 days of lecture a week. I don't want to necessarily cram everything into one long lecture. So keep an eye out for those, and I'll be seeing you guys in lab this week. Hope everybody's doing well and staying safe. Alright, later.